Our first unit will be all about these things called limits, and understanding limits will really be essential to understanding all of the big key ideas within calculus. To get us started, to figure out what exactly a limit is, let's take a look at the function f of x equals x squared minus 1 over x minus 1. F of x equals x squared minus 1 over x minus 1. It is really easy to just plug into this function and find f of 2, f of 3, f of just about anything. It is really easy to find f of 2, f of 3, f of anything, but not, there's a particular value you're not allowed to plug in. What is that value, and what's the problem? The issue is you can't plug in 1. You can't find f of 1. And if you said the problem is because plugging in 1 makes the denominator 0, absolutely it makes the denominator 0, that's an issue, but it's actually even worse than that. Because if you plug in 1, you get a 0 on the top and a 0 on the bottom. You get 0 over 0, which we're going to see over the next couple days is a little different than if we get 5 over 0. Anyhow, we've got a problem. We cannot find f of 1. Let's take a look at the graph of this thing. And don't worry about where exactly I got this graph from. We'll see that over the next couple days as well. Let me just show you what the graph is, and then we'll try to interpret what exactly is happening here. If I graphed that function, f of x equals x squared minus 1 over x minus 1, I would get something that looks like this. That's my function f of x. There's a hole on the graph at x equals 1. And by the way, throughout this video, and really all these videos we're going to go through, please make sure if I'm going too fast for you, you pause, finish your notes, and then kind of restart. So first of all, there's a hole at x equals 1. F of 1, what is f of 1? Well, what happens when we try to plug in 1 in here? Nope, can't do that. And if I look at the graph, go over to x equals 1, go up to the graph, there is no graph there. I have to say f of 1 is undefined. F of 1 is undefined. However, instead of talking about what's happening right at x equals 1, we can talk about what happens to the y values on the graph as the x values get really close to 1. As my x values from both sides are getting really, really close to 1, my y values are getting really, really, really close to 2. Therefore, this idea of as the x's are getting really close to something, the y's are also getting really close to something is the key idea behind a limit. And my limit will exist here, even though f of 1 does not. So I'm going to write, but the limit of the function, guess I really could have just said f of x, as x approaches 1, does exist. The way I'm going to write this, LIM is my symbol for limits. I want to show the limit as x approaches 1 of that function, f of x. And again, what I'm thinking about here is as my x values are getting really close to 1, just not right at 1, what are my y values getting really, really, really close to? Looks like those y values are getting really, really close to a height of 2. And therefore, I'm going to say the limit as x approaches 1 of f of x equals 2. And I think I actually want to write down that language so you guys can kind of see it and get used to how we say things like this. We're going to say that the limit as x approaches 1 of f of x equals 2. the limit as x approaches 1 of f of x equals 2, because, again, as my x values are getting really close to 1, those y values are never actually going to equal 2 because of the hole there, but they're going to get really close to a y value of 2. Let me give you kind of a more formal definition of a limit here. Definition. If, as x approaches some particular value c, in this case I was approaching 1, from both directions, from the left and the right, if, as x approaches c, some particular x value, from the left and from the right, the f of x values, or the y values, approach a single number, L. So the f of x values approach a single number, L. Then we would say the limit as x approaches c of my function f of x equals L. If, as my x values are getting really close to one particular number, in this case I was approaching 1, my y values from both sides are also getting really close to a particular number, in this case 2, I would say that that number they're getting really close to is my limit, and it's L. I'm going to show you a whole bunch of examples of this stuff, starting by looking at some graphs of these things so we can really try to understand this definition a little bit better. One thing I do want to add in, though, one little note. We do not care about what exactly is happening on the graph right at that particular x value, just what happens as we get close to the x value. You know, and I'm not going to bother writing that down. You heard it. We'll kind of see that in a couple of examples. Again, if you need more time to copy that down, please pause the video. So moving into this first unit and first chapter in your textbook, we're going to take a look at section 1.2 about how to deal with limits graphically and numerically. Graphical and numerical limits. And remember that from our Intro to Calculus little slideshow, I explained to you that everything in this course we're going to look at from a bunch of different perspectives, from formulas, from graphs, from tables of values, verbally and words. We're going to deal with how we look at these things graphically and numerically. Let me start by giving you a function that looks like this. And I do apologize, you are going to be doing a little bit of kind of freehand graphing your notes. Whatever, we'll be okay. After these 4 examples, there won't be too much of that in the notes. Let's take a look at a function that looks like this. Which hopefully you remember from Algebra 2 is probably defined by an absolute value function. I want to find the limit as x approaches 3 of my function f of x, and I also want to find f of 3. And these are 2 very different questions. Why don't I actually start with f of 3? F of 3 is just asking us, right at x equals 3, what's the y value on the graph? Well, let me look. 1, 2, 3. My y value is -2. F of 3 is -2. The limit as x approaches 3 of f of x, I'm going to think about this a little bit differently. I don't care about what's happening right at x equals 3. I'm going to even kind of cover that up. I care about what happens as my x's are getting really close to x equals 3. So from the right side, as my x's get really close to x equals 3, it looks like my y's are getting close to 2. From the left side, looks like my y's are also getting close to 2. Looks like, even if I ignore what's happening right there, my limit, sorry, I think I might have said 2. I meant -2. My limit as x approaches 3 of f of x equals -2. Even though these have the same answer, I need to think about them in very different ways. This one I'm thinking about right at x equals 3. And the limit, I don't care about what's happening right at x equals 3. I care about what y value I'm approaching as the x's get close to 3. So how about as x approaches 3? But not right at 3. In this case, the limit and the f value were the same, and that's always going to be the case if I want to try to find a limit at a particular place where my function is continuous. So I'm going to label this graph as something continuous. Let me show you another example. Let's take a look at something like this. Switch the order this time. I'm first going to try to find f of 3, and then I want to find the limit as x approaches 3 of f of x. F of 3 is asking the question right at x equals 3. What's the y value on the graph? And what is it? Hopefully you realized it's undefined. Actually, I probably shouldn't say f of 3 equals undefined. I'm going to say f of 3 is undefined. We don't have any graph there. However, the limit is not. I would like you to try to find your limit. What y value are we getting close to as the x's get close to 3? Hopefully you're saying 3. Now, what if instead I change the graph just a little bit and put a point over there? F of 3 now, that's changed. F of 3 is no longer undefined. When x equals 3, what y value do you have on your graph? Should be 5. So I'm going to change this. I'm going to say f of 3 equals 5. How about the limit? Has that changed? No. Remember, I don't care about what's happening right at x equals 3, so I'm going to cover up the x value right when x equals 3, and my y's are still getting close to a y value of 3 there. 2 more of these. Oh, by the way, I'm going to call this problem a hole. I do want you to get used to this language. Let's take a look at a graph like this. And I'm going to call what I just drew a jump. I want to try to find f of 3, and I want to try to find the limit as x approaches 3 of f of x. F of 3. Right at x equals 3, what value do we have in the graph? Well, right at x equals 3, open circle, yeah, there's no value on the graph. I've got to say f of 3 is undefined. But how about the limit? As x approaches 3, as x gets close to 3 from both sides, what y value am I getting close to? Well, I've got a problem, because I'm getting close to 2 different y values here. From one side, I'm getting close to 1. From the other side, I'm getting close to 4. That's not okay. Remember, our definition said we have to approach a single value. I'm approaching 2 different numbers. What I have to say here is the limit as x approaches 3 of f of x. The language I'm going to use is does not exist. That limit does not exist, which sometimes I'll just abbreviate as DNE. Let me ask you this. What if I change this graph a little bit by just, I don't know, maybe filling in that dot over there, making that a closed circle? If I do that, I would like you to take a moment and figure out f of 3 and the limit as x approaches 3 of f of x. See what you can do. F of 3, what's the y value on the graph when x equals 3? 1, 2, 3. Well, my y value is 1, 2, 3, 4. It's filled in over there. It's going to equal 4. My limit, though, I don't care about what's happening right there, so it really doesn't matter that I filled in that point. I'm still approaching two different y values from the two directions, so I still have to say that limit does not exist. One more, and then you're going to practice a little bit of this. Let's take a look at a graph. That looks like this. First of all, what's going on at x equals 3? Hopefully you're remembering that word asymptote. There's a vertical asymptote over here. So we need to find f of 3 and also the limit as x approaches 3 of f of x. Well, right at x equals 3, I don't have graph anywhere. F of 3, that's undefined. What about the limit as x approaches 3? Well, as x gets close to 3, from the left, it's going way up, not really getting close to a number. From the right, it's going way down, again, not getting close to a number. This limit also does not exist. In a very different way that the jump problem did not exist, but still does not exist the same. By the way, in terms of language, when a function value isn't there, we say it's undefined. But when a limit value isn't there, we say that limit does not exist. You're going to take a look at a couple practice problems, and then we'll come back and take a look at some numerical limits in the next video.